Hey guys, I want to talk about how you can build each of these three elementary logic gates, the NOT gate, the AND gate, and the OR gate, by only starting with the NAND gate. So it's a pretty cool thing because, starting with this one gate, we can build these three gates, and it turns out that NAND gates are really cheap to mass produce, so it works out well if you specialize in NAND gates and mass produce them, and they're cheap, and we can end up having all of the functionality that we want. So, okay, the way to produce each of these elementary logic gates is to wire the NAND gate up, the NAND gates up in different ways. And I want to go through the way that they're wired up and look at the truth tables and prove to ourselves that the wiring, in fact, leads to the right outputs. So let's start off with the NOT gate. This right here is the NOT gate. And let's look at what's happening. So let's consider there's only two possibilities for the inputs. It can either be on or off. And let's look at what happens when the input is on. So when the input is on, let's zoom in here. It's as if there's electricity, well, it is where there's electricity flowing through here. And what ends up happening is we can think of it like this. Let's use a 1 to denote electricity, being flowing through this area. So it starts off, there's electricity flowing through here, and it ends up being forked up and down. So there ends up being electricity over here and electricity down here. Whoop. Yeah. So we end up in a situation where when we're considering this initial input over here, let's just fix this. When we're considering this input, we end up in a situation that's basically this, where we have a NAND gate with both inputs being on. And with the NAND gate with both inputs on, the output is 0. So we're going to have a 0 here. And this aligns with what the truth table for NOT says, that when the input is on, this one, the input's on, the output is going to be 0. Okay. Now, there's one thing that I was wondering, just because I ask these sorts of questions, and this is the kind of person I am. So let's zoom in. And when there's electricity flowing through here, you'll probably have noticed that this path is longer than this path. So I like to think of it, imagine that there's like two people jogging together. They're going out for a jog, two friends going out for a jog. And they're jogging this way, and the first friend is going to take this path, and the second friend is going to take this long path. So the first friend is going to end up here first, and the second friend is going to end up here a lot later. And that's a little screwy. So that makes me think that we would end up in a sequence. So first this situation, and then this situation. I didn't see, because they arrive at their destinations at different times, how do we end up here? And basically the answer to that gets more into like physics and stuff. And also note that the wiring of the gates don't actually look like this. I mean, this is just showing these sharp perpendicular like lines. That's just for the diagrams. That's not necessarily how the wires actually are. But basically, yeah, if you want the answer to that, go do electrical engineering. And for computer science, just trust that it ends up reaching the destinations at the same time, pretty much. And you end up in the situation where you have two ones. Okay, let's also, just for completeness, let's consider what happens in the NOT gate when the input is off. So we're going to have the input be off. Well, there's not going to be any electricity flowing through here or here. If there's none there's none coming in this way, there's none going to be here or here. So we're going to end up in a situation where the NAND gate has 2 zeros for its input, and the output there is 1. So when we are now here, where the input for the NOT gate is 0, the output is going to be 1. So here we've proved that by wiring up the NAND gate like this, by doing this fork sort of thing, we end up with the functionality of a NOT gate. So we basically built a NOT gate from a NAND gate. Now let's look at these other two elementary gates, the AND and the OR. So I'm not going to go through every single possibility. I think you should do some of that yourself. It would take a long time to really go this slow and go through each possibility, but let's go through some of them. So let's look at the AND gate. Let's start off with both inputs being off. So, alright, when both inputs are off for this AND gate, we have 2 zeros going into a NAND. Then the output of that's going to be a 1. Okay. This is going to be a 1. Then this 1, the electricity here, is going to split up and down. So we're going to have a 1 here and here. And now we have another second NAND gate where we have 2 1s. And the output of that NAND gate is going to be a 0. So, to take a couple steps back, we had an AND gate where we put 0 and 0 as the inputs, and the output we got was 0. And we walked through the flow of the electricity and saw that this is actually what's happening. Okay, let's look at another example for AND. Let's look at when AND has a 1 and a 1. So the AND gate starts off with 1 and 1. We have a NAND with 1 and 1, so the output of that's going to be 0. Since there's no electricity flowing through here, there's going to be none here or here. And then we have a second NAND where we have 0 and 0, and the output of that guy is going to be 1. And to take the step back and look at the bigger picture, we have an AND gate where the input is 1 and 1, and the output is also 1. Alright, let's do one more example for the OR gate. This one's going to take a little bit longer. So let's do one example. Let's do this one, 1 and 0. So let's do this. We're going to consider the example where the inputs are 1 and 0, like this. All right. So the A is going to have a 1 and a 0. A is 1, B is 0. So, whoops, sorry. All right. So because there's electricity flowing through here, there's going to be electricity here and here. And because there's none here, we're going to have 0 here and here. Okay, so for this first NAND gate, we have a 1 and a 1, so we're going to have a 0 here. 1 and 1 leads to 0. For the second NAND gate, we have a 0 and a 0, and that's going to lead to a 1. Okay, so this 0 is being fed into this NAND gate, this 1 is being fed into this NAND gate. So when we have a NAND gate with a 0 and a 1, the output is a 1. Okay. And to take a step back, once again, we are in this situation where we have an OR gate with inputs of 1 and 0. And you see that here, input is 1, input is 0, and the output is going to be a 1. So I, in this video, went through, I think, this situation, this one, this one, this one, and this one. But if you want to fully prove to yourself that these implementations lead to these elementary logic gates, you can go in yourself and do the same thing that I'm doing and go through the truth tables, follow the flow of the electricity, write these ones and zeros in, and prove to yourself that by wiring up the NAND gates like this, they end up making these elementary logic gates. And to a little bit, this is a sort of a separate topic, but let me talk about abstraction and implementation. I want to do this. Well, no, I don't need to do that. I'm going to slice this like that. I'm going to drag it. Okay. So we have, let's consider two different views. There's the view of this and the view of this. Basically, this wire here corresponds to this. This wire here corresponds to this, and this wire corresponds to this. But here we're seeing a lot of these inner details, and here we're not. It's all like inside this thing. And we can visualize it like this. Okay, so everything inside of this gray box corresponds to everything inside of here. So let's zoom in a little bit. This little snippet here corresponds to this little snippet here. And this little snippet corresponds to this outside of the box. And this little bit corresponds to this. So you can see that by feeding in these inputs to this box, we could just think of it as a black box and think of the abstraction of these inputs lead to these outputs. Or we can think of it as actually there's wires and gates and stuff inside of here, and they're flowing around in this order, and it ends up leading to this output. So the abstraction is to just think that these inputs lead to this output. The implementation is to actually look inside the box and see how the wiring leads to the output.